Good evening, friends. This is Manish Khandelwal. I am a mechanical engineer, and the details of my experience are mentioned at the bottom of the slide. The name of this channel is Factory Forward TV. I am running one more channel with name Brainy Builders. This channel is suitable for students studying in class 6th to class 9th. Last week also I made a presentation on SPC, which focused on normal distribution of the data and standard deviation. This week I am making presentation on some more topics of statistical process control. In this presentation I shall be covering variation in data, fishbone diagram, Pareto chart, control limits, process capability, etc. Friends, each process has variations. The variation in the process can happen due to common cause or due to special causes. If the variation in the process is happening due to common causes, then the process shall be considered as stable process. The spread of the normal distribution curve, it may be noted here around the mean, is consistent over a period of time. The stable variation in a process can happen due to environment like change in temperature or humidity or air quality. It may happen due to difference in machine setting, normal wear and tear of the parts, variation in the maintenance of the machine. It can also happen due to operators' skill, training provided to them. The tolerances and the specification of the process are also reasons for stable variation. On the other hand, the variation in the process may be due to special causes also. In such cases, the process shall be considered as unstable process. It may be noted here that the spread of the normal distribution curve, this is less, this is more, this is in between, is different at different time. The location of the bell curve is also changing. The process in such condition shall be considered as inconsistent or unstable process, as we said before. Unstable variation in the process can happen due to malfunctioning or breakdown in the machine or some unnoticed heavy wear. It can happen due to lack of attention or SOPs or standard operating procedures being not followed by the operators. Bad quality of electricity like fluctuation in voltage or compressed air, or quality problem in raw material is also a reason for special causes which are resulting into unstable process. So how to identify the variation? The variation are identified by statistical process control, which is used to monitor and control a process. Here we first collect the data. We have to make it sure that the data is accurate and is representing the complete process. Then we make cause and effect diagram. This is also known as fishbone diagram because of its shape. In this we select the output which is deviating from the desired outcome. Then we categorize the potential causes for this deviation in 5 M's and environment. 5 M's are man, machine, material, method and measurement. These are 5 M's. After this we make Pareto chart. This chart is to identify and prioritize the sources of variability. It is also known as 80-20 rule, which states that roughly 80% of the problems are due to 20% of the reasons. So you take action on these 20% of the reasons and you will solve 80% of the problems roughly. Finally, we make control chart. These charts are used to monitor the performance of the corrective steps identified here. Control charts also help us identify variation when a process goes out of control or there are some special causes. Now, what is a fishbone diagram? This fishbone diagram is also known as Ishikawa diagram because of the name after this gentleman invented it, or cause and effect diagram. So these are the causes and this is the effect. We do the root cause analysis for this. So first, what is the problem? We write here. After that, as we said in previous slide, we divide the reasons in man, machine, method, material, measurement, 5 M's and environment. And after that, we write the sub causes. For example, training we can write, or not following the SOP we can write. We can write about the machine wear and tear or maintenance, or we can say the method we are not following the SOP, the method was wrong, or we can say these material supplied by the supplier was not correct, or the measurement taken was not correct, or the temperature or the humidity was more, which is affecting. So these causes we write here, and then of course we select as to what are the causes and how to take action on this. This is for the benefit of the people who want to make fishbone diagram looking like fish. So once we have made fishbone diagram and analyze that, we can make a list of potential causes which are causing the variation. So for example, there were 10 causes which are causing the variations. Rejected quantity against each cause is also written here. So we make this table. Here we are writing cause number 1, 2, 3 up to 10. Then the rejected quantity against each cause. Then we make a column and take the cumulative quantity. For example, here 380. Next is 380 plus 300. Cumulative quantity 680. Similarly, again we add 130, 8, 110, and like that we come to the end 978. Then we take the cumulative percentage, 380 upon 978, it will be 39%. 680 upon 978 will be 70%, and we go down up to cause number 10. Making this table, we make Pareto chart. I'll show you in the next slide as to how to make the Pareto chart in Excel. Just to understand it, you can see that two causes, cause number 1 and 2, are causing 70% of the rejections. So these two causes only are causing 70% of the rejections. That means if we resolve this issue, cause number 1 and 2, if we resolve, then we can reduce the defects by minimum 70%. Maybe some actions are taken and the rejections in other areas are also reduced, but minimum 70% we can reduce if we take action only on these two. So this is the benefit of the Pareto chart, that we can prioritize the actions taken. Now let's see how to make Pareto chart in Excel. First, after analyzing the fishbone diagram, we make a list of potential causes which are causing the variation. So for example, these are the 10 causes, 1 to 10, we write it in a column. Against each cause, we write the rejected quantity. These are the assumed quantities. After that, we find out the cumulative quantity. This is achieved by adding the previous quantities. So 380 is 380. Then next one is 680. So 300 plus 380, 680. Then third is 130. So this cumulative quantity is 810. 130 plus 300 plus 380, like this. So up to 978. So you can say total rejected quantity is also 978. And last column is the cumulative percentage. So this we achieve, say 380 divided by 978. So 39%. 680 divided by 978 is 70%. So like this. After that, we select all these 4 columns, go to insert, and then select the 2D column. Once you do that, you will be getting a chart like this. This brown color is cumulative total. This we don't need, of course, we will remove it later. Then we left click on this chart and then we get change chart. When we click this change chart, we get a window like this. Here we take the cumulative percentage on the bottom, and on the top we select clustered columns line on secondary axis. On the second, this is called secondary axis. So we select this. Then we get a graph like this. This is a Pareto chart. And these columns can be deleted. We just select one, all will be selected and just deleted. So this cumulative total will be deleted and we get a fine Pareto chart. This is how we make a Pareto chart in Excel. Let us understand what are specification limits and control limits. So specification limits are basically voice of customer, what our customer wants. So the purpose of specification limit is to ensure that the final output meeting the customer's expectation with respect to quality. For example, let us consider a manufacturing process is making steel bottles. The specification limit for a 500 milliliter bottle is 250 grams plus minus 10 grams. That means all the bottles which we are producing, if they are falling between 240 to 260, then these are falling in specifications limit and these are meeting the customer requirement. Any bottle below this weight or above this weight is out of spec. That means it is not meeting the customer expectations. Then are the control limits. These are different than the specifications limit. Let us understand. Control limits are statistical boundaries used to monitor and control the stability and variation and help identifying the special causes. What we do here is that we find out upper control limit and lower control limit with the help of mean and standard deviation. If the data points are falling between upper control limit and lower control limit, then we say that our process is under control and there are only common causes which are causing whatever variations there are. But if the data points are going above UCL, above upper control limit, or below lower control limit, then that indicates that there are special causes available in the process. Once the data is collected, analysis is done through Ishikawa diagram and the activities are prioritized through Pareto chart. We make control charts. Control charts were invented by Dr. Schwart in 1920s, more than 100 years ago. These are used to predict the expected range of outcomes from a process and determining whether the process we are running is stable or not. These two are the main objective. Now, we can have two types of data. One is continuous, second is attribute. Continuous data is having a numerical values like 2.2, 2.3, 5, 6, 7, all numerical values. This is a continuous data. Whereas attribute data is non-numerical values that can be classified in yes, no, or good, bad, okay, not okay. And this continuous can be further classified in individual measurement, subgroup data, then this is individual moving range chart, X bar chart. Attribute of course is total defect, and then we make P chart, U chart, C chart. We are in this presentation concentrating only X bar R chart, which are the most popular in the industries. We will not discuss other charts. Let's understand X bar chart, R chart with an example. This is an example. We are taking data of 5 samples. These are the samples A1, A2, A3, A4, A5. And we are taking the observation 10 times. First we find the X bar, that is the average. X bar is average of all observation of samples. So these are the samples. When we take the average of this is coming 3.08. This is the X bar. Similarly, we take the X bar of all the observations and we find out these values. Then we find out range. Range is nothing but difference between maximum value and minimum value. So here the maximum value is what? 3.11, minimum is 3.05. So the difference is 0.06. Similarly here the maximum is 3.13, the minimum is 3.05, difference is 0.08. We go down further, maximum here is 3.10, minimum is 3.06, so difference is 0.04. Like this we find out the range. Now further we take the average of X bar. This will be called X double bar now. This comes to 3.08. And when we take the average of all the range, this is called R bar and it is 0.05. Now we start preparation for X bar R chart. To make X bar R chart, we need to know upper control limit, center line and lower control limit. So center line is nothing but the average of average, that is X double bar. This is the center line. So this is 3.08. I have taken one more decimal plate. So this is 3.082 is the center line. For calculating upper control limit and lower control limit, we have to find out the standard deviation first. Standard deviation of this data. So standard deviation sample within bracket, we put this data and the result is 0.004756. So we'll use this standard deviation for making X bar chart. Similarly, for making R chart, we take the standard deviation of R data. This is coming 0.026687. So we'll use these two data. For X bar chart, UCL, that is upper control limit, is X double bar plus 3 sigma. So X double bar is 3.08, 3 sigma is 3 into sigma 0.004756. That comes to 3.0961. This is the upper control limit. 3.096. This is the upper control limit. Similarly, for lower control limit, we'll just change this sign from plus to minus and the value will be 3.0675. This is the lower limit. We'll make the graph using these data in the next slide. Similarly, for R chart, we calculate UCL. This is D4 into R bar. D4 is a constant and the value of D4 is given here. It can be found out anywhere in Google and all, you can find it out. So this D4, and how many samples are there? 5. So these are the number of samples. So 5, D4 is 2.114. So D4 into R bar, 2.114 into R bar is 0.05. This comes to 0.1057 or 0.11. So this is the upper control limit. LCL is D3 into R bar. D3 is what? For 5 samples, 0. 0 into 0.05, so that is 0. So lower control limit is 0. You will find that D3 is 0 up to sample 6. If you are taking 6 samples, then LCL, lower control limit in R bar chart, shall be 0. Secondly, UCL and LCL for X bar chart can be calculated using formula X double bar plus minus A2 into R bar. X double bar plus A2. A2 is this. For example, in this example, A2 is 0.577 because there are 5 samples. 0.577 into R bar 0.05. If this is a plus sign, then we will get the UCL. When we convert this plus to minus, we will get the LCL. So this is another method of getting the UCL and LCL for X bar chart. Now, how to make X bar chart, R chart? Please be very careful here. Let us filter the relevant data only. Let us take X bar. X bar was the mean of all the observations. Then upper control limit, center line, this was X double bar. Then the lower control limit. If you plot the graph and plot this data, then we will find that this data is moving between upper control limit and lower control limit. My upper control limit is 3.096 and lower is 3.068. Mean is 3.082. So my all the data are coming between this. This shows that there is no special cause available in my process and my process is in control. If you see this bell curve here, different colors are showing the sigma. So first sigma, one sigma is blue, then another sigma is green, another sigma is yellow. Similarly on the other side. So 3 sigma and 3 sigma. If you recall the formula for UCL, it was X double bar plus 3 sigma. Then LCL was X double bar minus 3 sigma. So if my process is between plus minus 3 sigma, then I will say that my process is under control and there is no special cause available. But if any observation goes above upper control limit or goes below lower control limit, then this shows that there are some special cause available in the process. We need to mark that and take action. Very similarly is R bar chart. R bar chart, LCL is 0. UCL we calculated 0.01 and the center line was 0.05. And here also all my data are coming between the UCL and LCL. So this is also in control. Friends, let us understand few rules to interpret a control chart. Let us assume that this is a mean and we have 3 zones on either side of this mean. 1 sigma, 2 sigma and then 3 sigma. Similarly on the bottom side, minus 1 sigma, minus 2 sigma and minus 3 sigma. So the rules are, if any point is falling outside 3 sigma, whether it is plus side or minus 3 side, then it's an alarm. Or if 2 out of 3 points are in zone 3, we can call it zone 3. So if in this zone we have 2 out of 3 points, whether in minus side or in plus side, that means it is having a potential to go out of this zone. One more rule is that 4 out of 5 points if they are in -2 sigma zone, that is also an indication that the process may go out of control and we need to be careful. 4 out of 5 point in zone 2, whether it is in plus side or in minus side. Then 8 or more points are on one side of the center line, whether it is in zone 1 or zone 2 or zone 3 or clubbed together. But 8 or more points, if they are on one side of the mean, then this is also an indication that something may go wrong. And the last rule is that if there is a trend of 6 or more points increasing or decreasing, if 6 or more points are in decreasing nature or they are increasing, that is also a signal that there is something wrong. We need to be careful. So this is how we can interpret a control chart. What is process capability? There are two types of statistical process capability indices. One is CP-CPK. CP is process capability and CPK is process capability index. The other one is PP-PPK. PP is process performance and PPK is process performance index. Both above can be determined using the same formula. However, CP-CPK is calculated to find out the potential process performance in long term, whereas PPPK is used to find out the actual process performance and therefore it is for the short term. So once the process is set, everything is running fine, then for routine we calculate PPPK. For CP-CPK, if we are developing a new process, then we need to calculate CP-CPK, or if there are some major changes in the existing process, then also we need to calculate CP-CPK first. Similarly, if there is some major overhauling in the machine or some modifications in the machines have been carried out in the machines we are using for the process, or there is some change in the raw material constraints or change in design of the raw material, or we are adding some new suppliers for the same raw material, or if there is some substantial change in the environment, temperature, humidity, in that case we need to calculate CP-CPK. PPPK is suitable for short-term process monitoring and performance evaluation, as we discussed before. CP-CPK is mostly talked about in industry, so we shall be discussing only CP-CPK in this presentation. Now, what is CP? Process capability. Process capability measures the potential capability of a process to consistently meet the specification limit. So CP is equal to USL minus LSL, that is upper specification limit minus lower specification limit divided by 6 sigma. Let us take 3 different scenarios to understand process capability better. Let me write the process capability formula once again. CP is equal to USL minus LSL upon 6 sigma. Upper specification limit minus lower specification limit divided by 6 sigma. In all the 3 cases, it is assumed that the process is centered. That means the spread of the data around the mean, right side and left side, is mirror image. In the first case, CP is equal to 1. If CP is equal to 1, then USL minus LSL is equal to 6 sigma. Just put CP is equal to 1. Friends, if you recall empirical formula 68, 95, 99, which says that in the normal distribution curve, 99.75% of the observation fall between plus minus 3 sigma potentially. So if CP is equal to 1, then 99.75% of the observations shall fall between upper specification limit and lower specification limit. We can also say in this case that it is just meeting the customer's requirement, just touching. Now let us take another scenario. When CP is less than 1, of course the process is centered here also. In this case, upper specification limit minus lower specification limit shall be less than 6 sigma. The spread is going out of specification limit. So the data falling here, which is marked with red, shall be rejected, indicating that some correction or corrective action is required here in this process. But if the CP is greater than 1, it is more than 1, then we are more comfortable. We shall be having lesser rejection than what we had in CP is equal to 1. We are more comfortable here. Let's see few things more on CP-CPK. Assume that there are two curves, A and B. They are having the same spread. These are the upper specification limit and lower specification limit. I have just shifted this graph just to show that there are two curves here. Now the second curve B, the mean shifts. Mind it, only the mean has shifted. The spread has not changed. The specification limits have not changed. Now in this, since the spread is same, but the mean has shifted, some of the observations have gone beyond upper specification limit. So this is the rejection. But if we calculate the process capability CP, CP says USL minus LSL upon 6 sigma. So USL has not changed, LSL has not changed, spread sigma has not changed, so CP is remaining same. How to catch it? Here the process capability CPK will come into the picture. Mind it, CP is not considering the mean at all, whereas CPK considers the mean of the data along with the spread. So to calculate CPK, we calculate first CPU. Here X double bar, that is mean of means, minus USL divided by 3 sigma, this portion. And then we calculate CPL, lower one, LSL minus X double bar upon 3 sigma. So in this we calculate CPU and CPL, and whatever is the minimum of CPU and CPL, that shall be called as CPK. So once again CPK considers both mean and spread, whereas CP was considering only the spread. So CPK is more accurate, I'll say, or it will tell about the process more. For example, the specification for an item is 11 plus minus 1 mm. So that means the tolerance is 2 mm. From 10 to 12, the product is okay. Now keeping all other things, if the process produces the item between 14 to 16 instead of 10 to 12, in this case there shall not be any change in the process capability CP, because here also it is producing between 2 only. We wanted the item to be produced between 2 plus minus 1, that is 2. Here the process is producing the item between 2 mm only, but the mean has shifted. Everything is rejected here. But CP will say our process is capable, whereas actually the rejection is happening. So when we have the CPU, CPL and then calculate CPK, then we'll come to know, oh, our process has shifted. instead of 10 to 12, it is making 14 to 16. So our process is capable, but the mean is shifted. This is the advantage of calculating CPK. Let us do interpretation of CP and CPK with the help of some diagrams. The first one is the spread is touching both upper and lower specification limit, and the spread is equal to always 6 sigma plus 3 sigma plus 3 sigma. So in this case, USL minus LSL is equal to 6 sigma. If you go by the formula, CP is equal to USL minus LSL upon 6 sigma. In this case, CP shall be 6 sigma upon 6 sigma, that is 1. So if the spread is touching both USL and LSL, in this case, the CP shall be 1. Now the other case is that the spread is limited between plus minus 2 sigma. So 1 sigma is left here, 1 sigma is left here. And as we know, the spread is 6 sigma. 6 sigma plus 1, 8 sigma. So USL minus LSL shall be 8 sigma. In this case, CP shall be 8 sigma upon 6 sigma, that is 1.33. In the third case, if the spread is between plus minus 1 sigma only, so 2 sigma is left here, 2 is here, and spread is 6 sigma. So in this case, USL minus LSL shall be 6 sigma plus 2, 10 sigma. So CP shall be 10 sigma upon 6 sigma, that is 1.66. And lastly, if all the data are converging on mean, in this case 3 sigma is left here, 3 sigma is left here, the spread, anyway there is no spread, but the value is always 6 sigma. So 6 sigma plus 3, that is 12 sigma. In this case, CP shall be 2. So if the data is normally distributed and the value of CP is coming 2, then we can easily say that all the data are falling on mean. So this is for process capability, CP. For CPK, there are 5 graphs. One is when the mean is falling outside the specification limit. If this is the case, then our CPK is going to be negative. Now, if the mean is just touching the limit, just touching the specification limit, in this case, the CPK is going to be 0. Third case is if the mean is between USL and LSL, but some of the data is falling outside limit. In this case, CPK shall be between 0 and 1. The fourth case is that the mean is between USL and LSL. All the data are between LSL and USL, but some data are just touching the boundary, just touching the USL. In this case, our CPK shall be 1. And next, if all the data are in between USL and LSL, the mean is also, of course, shall be between USL and LSL. In this case, the CPK is going to be greater than 1. So this is the end of this presentation. This was the second presentation on SPC. Hope I have covered all the important topics related to statistical process control. Your feedback shall help me giving better and better presentations. Please subscribe to my channel to get the prompt access to my presentations. Thank you.